This video is intended for entertainment and historical purposes only. It's not meant to be an instructional tutorial or provide professional advice. Today, we're going to be making a brand new set of steam locomotive rod bearings, commonly known as rod brasses, using a nifty technique that avoids costly foundry work or high-priced specialty materials. We're also going to be using an obscure hand tool known as a bearing scraper to finish off the rod brasses. But first, let's talk about the different types of rod bearings in common use. Regardless of their size or shape, steam locomotive rods generally use one of three different types of bearings. They're either roller bearings, solid bushings, or split bushings. Roller bearing rods are pretty self-explanatory, and they're only found on the largest and most modern steam locomotives. So let's just gloss over them. Solid bushing rods are easy to spot, as they're made in one piece and usually have a big nut and washer, or an eccentric crank that secures them to the crank pin. And like the name implies, they literally have a solid bushing that's either pressed into the rod or floating between the rod and the crank pin. And then there's the split bushing design, which we'll be making today. As with anything, there are pros and cons to either style of rod brass. Split bushings are more complex and costly to manufacture and maintain. However, they can be adjusted as they wear in, and can easily be mended if they've experienced overheating. Compare that to solid or floating bushings, which are quicker and cheaper to manufacture and replace. However, they can't be tightened up as they wear, and if you overheat one, it'll become a worthless piece of scrap in the blink of an eye. I want to clarify that in railroad speak, every material that's yellow and shiny is generally referred to as a brass, regardless of its actual composition. And rod brasses are no different, since they're actually made from some type of bronze rather than brass. For those of you who'd like to see an extended cut of this episode, which goes into slightly more detail, check out my Patreon or YouTube memberships page. Now, let's head into the shop and get to work.
This is a brief discussion about steam locomotive brasses. They're referred to as brasses, but they're actually not. They're bronze. The proper steam locomotive bronze that to make crown brasses, hub liners, big ends, slippers for crossheads, all the same material. It's called 80-10-10, which is 80% copper, 10% lead, and 10% tin, sometimes referred to as a high-leaded bronze. And you can tell it's very copper-colored. It's good stuff. These are the original brasses off of the Davenport engine. They're pretty tough. They were just put together, hacked together, and put in. The attributes of 80-10-10 is that it can withstand occasional loss of lubrication. It can withstand some dirt entrainment. It's soft enough to encapsulate the dirt into the bearing. And it can withstand misalignment of bearings because it's fairly plastic. It's fairly soft. And if that doesn't say steam locomotive, I don't know what does. When you go to the supplier to try and find this stuff, this 80-10-10, they're going to try and sell you 660. 660 is an automotive brass that's readily available. It has a problem in that it contains zinc, and it's too hard and not ductile enough for steam locomotive use. You need to get the proper material, especially for crown brasses and that sort of thing, and big ends. This is the stuff to get. I've gone ahead and broken all the rules, of course, and made a brass out of what was available to us. We're rebuilding these engines on a budget, and we found some naval bronze, which is, as you can see, is quite a bit different color, and it's not as good a material for brasses. So we're going to go down, get some pieces cut up, and start making brasses like this. 2 more of these, 2 more of these.
Before we get into that, do me a favor and hit that subscribe button. Remember, it doesn't cost you anything to subscribe, but it sure helps grow the channel. Now let's get back to it.
So here we are, parting off pieces off of a bronze bar called a billet. There's a piece over there already cut off. So what I'm doing is I'm parting off the material here. Just you gauge the cross feed, and we let the machine start doing it. And it is a paintbrush because this stuff wants to fly all over the shop, and so you use a paintbrush to just make it drop down where you're saving the bronze. So we've gnawed this down with the parting tool. I left a little tiny piece in the middle, because if you go all the way across and this falls down, you can never catch it. It's heavy, and it'll pinch your fingers under here. This is the voice of experience, so you just bend it back and forth. You can see how ductile this stuff is, because I have to bend it quite a bit to get it to actually break off. So here's the rogues gallery of bits and pieces that we're actually going to make all the brasses out of. These are the 4 pieces of bronze rod, a bar, that are going to make this up. Each piece makes this half. As you can see, it's barely big enough. This corner and this corner and around the other side. So the first thing to do is to slab them, get them down so we got some square surfaces. So what I've done is I've marked the middle and I've measured out each edge. They're going to go in the chuck, the 4-jaw chuck, and I'm going to machine them down to these marks so that they're square. So this is the finished face, and it's going to get sweated to another block. To get them to sweat straight and level, you need to hollow this just a bit, because this is the finished surface, so where the 2 brasses meet together. And you don't want them twisted or cockeyed anywhere. So you just take the tool and run it into the material just a bit. And that makes a cone that won't be rocking. It won't have any high point. So this is the next step. Brasses are always machined, soldered together in one billet, one piece. This is still soldered together. You can see the solder line. Everything is done. Everything is fitted. It's fitted in the bore. Everything's happy. And the last thing you do is you heat it up and separate the 2 pieces. So these 2 pieces are going to get soldered together. They have been machined accurately. They've been cupped out in here. I've got them marked so that I don't get them in the wrong side. And basically you just lay them on a block this way. Put some flux in here, some solder, and heat them up and stick them together very accurately as you can. I use 50-50 solder, 50% lead, 50% tin. The modern solders don't work so well in this application. And you end up with a piece that looks like this in one piece that eventually turns into this piece when you're all done. And you put it back in the lathe and you machine these edges off, and everything stays fixed. There's no messing around. You can see how much you have to take off. And then you proceed to the mill and cut all these surfaces out. And the last process is to turn out the bore. You can see how the solder is supposed to squelch out. You can probably see the solder line here. Not much. And now I'm blocking them off. I'm going to shave these sides off on both sides till I have a square piece, the shape of the rough brass, and then we'll move to the milling machine. So these are the finished blanks that we're going to make some more bearings out of. I don't know if you can even see where they were soldered together. There is a line there, right here. The previous brasses I made were offset because it's been damaged, and I've made new parts and new piston rods, and I can make everything fit. But for this, the engine is all in good condition. It's all ready to go. It's just missing its rods. So we're going to replicate these original Davenport brasses, which incidentally actually would fit. They're the same size. The cheeks are a little bit longer here, and we'll just live with that because we're going to have to shim under here or under here to move this bearing back and forth within the strap so that the clearance volumes are correct. So we're just going to copy these. So the centers of the brasses have been laid out. We're using the parting line where the babbitt or the solder is, and equidistant from each edge. And I'm going to use the drill press to put in a center. That makes it easier to put in the lathe. With the 4-jaw, you just hold it up against the chuck with the dead center, and you can bring the jaws into to suit. So now we're going to set up, put the drill chuck in here. I'm going to punch through a pilot hole, and then an 1.25 inch drill, and then proceed with the boring bar. All right, we broke it through. Now we'll put the big drill in there and drill it out slow. So when you're drilling bronze, any non-ferrous material, you have to be careful. The drills are designed, this angle is designed for steel, and it will grab into the bronze and give you all sorts of grief. I grind these myself, and I've flattened off this angle here so it's flat. so it sort of scrapes rather than digs in, because it'll actually jam right in there if the blade is powerful enough. So we're going to put this in the center and offer it up to the work, and we'll drill this hole out so we can start boring.
So if it's changing, you know you're breaking through.
You notice now why, when you're working with bronze, it flies all over the shop. So now we've transitioned from drilling an 1/8 and an 1/8 hole through here, 1 and 1/8 inch. We've installed a boring bar, the same one you've seen before. The tooling has no rake. In other words, it's not wanting to dig into the material. It's square to the material that it's cutting. And we're just going to start boring. Now you'll notice that it's fairly slow because this is a perfect opportunity for the swarf, which goes inwards, to build up behind the chuck and come out these holes all over the place. If you turn it too fast, it goes a long ways. So I've got it about as slow as I want, and I'm just going to start taking cuts out until I get to 2 inches. So we'll do a couple of passes and you can see how it goes.
If you listen carefully, you can actually hear the bit hitting the babbitt into the billetted joints because it's softer. It makes it quick. So there you are. I'll just keep doing this whole process until I get them bored out.
So I've got the hole bored out to size, roughly machined a bit of an angle on here, and now I want to finish it. This is called a bearing scraper. It's used for fitting babbitt bearings and bronze bearings. It's basically a point. It's hollow ground in here, and it's sharpened by sharpening along this edge. It's like a knife. And one offers it in here and actually can scrape the bronze away to make this radius to fit in the fillet. Got a little bit of chatter here, got to weigh on me a bit, but you can see how that smooths up the bearing. These were used to fit machine tools. They were very much a hand machine back in the day, and we're still using them to fit bearings. Now this is where the fun starts. I have to take this brass out of the chuck and turn it around and put it in the other side so I can cut that radius. And of course, it never ever goes back exactly where it was. And so there's a fair fiddling or a bit of fiddling around to get this side the same as this side. The first thing I have to do is I got to clean all the swarf out of the chuck, because any little piece that's behind it will throw it off and it will not be accurate. When you're working with 4 jaws, I usually mark 2 of the jaws, and if I'm doing repetitive work, I only loosen 2 jaws at a time. That way you don't get too far out of whack. And we'll see what we got. As you can see, it's out around, so now I'm going to mess around and get this trued up so I can do that other radius. So what we're doing now is we're facing off the brass to get it to fit between the cheeks. And it was about 3 or 4 thou too thick. Well, it's probably going to be a little jiggery pokery just to actually fit the brass. It's important to remember that the brass is in 2 pieces, and if it's too loose, you can always file a bit off of these faces so it'll go together. But when it's finally fitted, these pieces should be tight together. There should be no gap in here, but these will fit fine. In fitting up brasses for steam locomotives, you have to remember that a steam locomotive is not a stationary object. It works in a very imperfect world. The wheels are going back and forth laterally up to 3/4 of an inch. The wheels are going up and down relative to each other, which causes a twisting motion on the journal. there's dirt, there's all sorts of different things going on. And so the clearances are fairly wide. I usually fit up brasses with somewhere around 10 to 15 thousandths of an inch clearance to make sure that nothing grabs. These, just to show you how much you can get away with, these are the original brasses replacements. Somebody fitted in the field. And if you can look closely, you'll see that the filing marks are still there. They only touched in a few spots. It was only actually touching on the back of the brass here. The rest wasn't even running. It eventually would break in, but you can even see how it was twisted because this was wearing here and over to here, whereas this corner and this corner. That means that the brass was probably tilted like this, or the wheel set was tilted, or really don't know what. But locomotives are really an imperfect machine, and they had to be machined to that regard. It's not like some fancy locomotive on beautiful track. We've seen some lovely examples of British locomotives and whatnot, all shiny as all get out and go like hell. But this is a construction engine, and it worked hard and very, very poor track and did the job without complaint. So you have to machine it to that with that in mind. So I'm starting the process of machining the brasses up to fit in the straps. They have to be reasonably accurate, but not too special. I've done a lot of these, and I've found that with this old machine, this old mill was from 1942, and it's kind of worn out, but it does the job. So I have very carefully machined this slot out to a 1/2 inch deep with a 1/4 inch wall. I kind of snuck up on it, took the time to do so, and now this table is locked down, and all I have to do this slot and repeat it is to just turn the block over. You don't turn the block end for end, you just turn it over, so that you don't turn the block over. The change for this face is the face you want to keep here. You want to turn it around. That's a couple of cuts, exactly where I want it. I cut in one direction. You may wonder why I don't just cut back. Well, when you go back the other way, it throws the brass all over me. The way it is right now, it's going into that shield and elsewhere and not on me. So that's why I only cut one way. So the brass has been done to size on one side, leaving a 1/4 inch wall. We're now milling out the other side to get it to 1.5 inches thick. So the brass has been turned all out, all the way around. As I said before, you don't turn the brass around, you just keep turning. I'm using the marked side, and I just keep turning it around. That makes it all accurate. It sort of compensates for the wear in the machine, so there's no real lip here. So I've now snuck up on this distance here, which is 1.5 inches, and I'm proceeding to mill it down. I'm going to do all the sides. So I've got this done. I've used this surface to know how deep to go here. There's maybe a 1/2 thou here, just the shadow. I've carefully measured this, that I'm exactly where I want to be, so now I can proceed to turn it over and do the other ends. And one quick comment, why I would do the ends first is that it's important to remember that these are soldered together and the solder line is here. And so this entire top piece that we're machining is supported by the solder. There's no vise, there's nothing else holding it, and it's kind of a disaster if it breaks loose. So to that end, I do the ends first. At least I have a thickness of material here in the joint that's strong enough, or should be strong enough, to hold it because it's trying to tear away. And then you do the sides afterwards because both ends are supported within the vise and the solder isn't really holding anything together. So we're getting close. This is a brass off of the other engine that has been fitted. It's got the oil hole milled in the top. It's got the slot in it for the set screw. And you'll notice this brass had a known center. This brass, I don't know what the center is for I'm talking about the clearance volumes on the pistons. So you can see the
The parting line is exactly the same, but this hole has been machined farther back. And this is only 1/2 inch deep here, whereas this is 3/4. And the whole idea here is that this is kind of a universal brass that's designed to be fitted when the engine's not around, like it's not here. This is the original Davenport brass as sent. You can see how much smaller it is. And it was the same. It was just a universal brass, but I felt these cheeks were a little bit short. When you ordered this from the factory, what you got was a brass that was roughly machined, and you fitted it with a file and a hacksaw. You can see that the oil hole's been cut with a hacksaw. The wherever it is, the clearance hole has been cut with a hacksaw and filed out. So these two brasses now are universal. They're designed to go in the rod and be moved back and forth until you've ascertained what the clearance volumes are, and then the back cheek gets cut off even with the back of the rod, because this is only 600 thou here. So this is pretty much a universal fit. This is a specific fit. What I'm going to do now is I'm going to mount these brasses into their respective rods, and right at the moment they will fit any way. They will fit one way, the other, doesn't matter. They're ubiquitous. I'll find out the best way they fit, and then I'll mill the oil hole and the relief for the set screw and what afterwards. And then when these go back up, these rods go back up to the engine and the clearance volumes are ascertained, the person will shim these one way or the other until they fit correctly, and then that'll be the last. And if there's too much hanging out the back here on this edge here, this is only 600 thou. This is 700. This is 750. So we'll see where that goes sometime in the future. So here's the finished brass, and so we're now going to heat it up and separate the two pieces. Everything else is done. I'm about to put this all together. These brasses generally are fairly tight fit in the strap, and they will loosen up. I'm just going to put it together for now. There's a shim that goes in the back of the brass, and its sole purpose is to allow the wedge, which is in here, to bear against it, and so it doesn't dig into the brass. So we got our key shim in here, and we just offer it onto the engine, and there you have it. I'm going to go through a Locomotive big end brass just finally. We have a key that bears on a shim that's inside here, a piece of steel. This brass can move back and forth, but if it has to go too far, we're going to end up having to mill more material out from behind here, or adding a shim in behind here, not sure what yet. It has tapered bolts, 2 lock nuts on the bottom. The small diameter on the lock nuts or the bolts is so you can hammer it back up without wrecking the thread. And this is a set screw that locks the key. So this is all assembled except for this last nut, the way it would go on the engine. And then it just has to be fitted. One thing I should say, there is no need on Locomotive brasses to cut oil grooves in here. That's something you do on stationary bearings that don't move. This bearing wabbles around so much up and down and back and forth that the oil is squeezed all through the whole thing. It doesn't need to have oil grooves in here. There's a lubricator goes on here, or grease, whichever you like. It goes through a hole that's in the brass here, and it just squelches out. And as the brass works on the pin, the oil or the grease squelches back and forth and sideways, and it gets lubricated just fine without oil grooves. The other thing is that when these brasses are correctly fitted, they're right tight. You don't leave them loose. If they're loose, that gets dirt and all sorts of other problems in there. These are supposed to be fitted so that they smack up against each other and they're tight. And then there's no need to be hammering away on the key. That's one of the biggest problems is some engineers think they got a knock, so the first thing they do is start hammering on the key. And if you got a space in here, you can over tighten the brass and it'll overheat. This key goes in until it's snug, you tighten the set screw and you leave it alone. And if it's knocking you and you actually ascertain that it is knocking, then you have to take the brass apart and you have to file some off this surface to bring it together. So we're getting down to the nitty gritties here. And right now I'm working on the wrist pin ends. The wrist pin it's soldered together, you can see it. This hole is a 1/2-inch hole that's been drilled in and reamed out and placed on a pin in the milling machine, put against a milling cutter. It sits like this, and you turn it to make this end. So this is a radius from this hole, and then it's manually finished. So now what has to happen is I have to actually drill out the hole for the wrist pin, and this is the last operation you can do because this is 1 3/4 inches and the pin is 1.5 inches, which means you've only got 1/8 of an inch of brass here. And usually what happens is that this solder that's in here, it gets kind of tough for it to hold things together. So this is clamped originally in the forejaw. It's drilled out on this center. This is the actual center. This will clean out to about there. And it will hopefully work out, and then you make the two pieces apart. And then the whole assembly goes up into the here, and this has to be fitted as well. This is tight. You don't want them moving. So they fit in there, and the wedge is in the bottom. But when they're all in bits, they're hard to fit. So you got to make sure everything's fitted before you separate the pieces. Because these are pretty small. I'm not used to working stuff this small. So this is where the sheep and the goats get separated. I'm not really very good at this really small stuff. And my hat is really off to those guys that build like 7.5-inch gauge, 7.25-inch gauge steam locomotives. There's no bloody way I could ever possibly do that. This is about as small as it gets for me. So what I'm doing here is I'm going to put a drill through. I'm going to put a bigger drill through, and then I'm going to bore this out to 1.5 inches. This is where it gets interesting because we're cutting into that other hole and it's an interrupted cut. You can see how a drill this big, even this size, wants to follow the line of least resistance. It wants to go towards the hole that's already there. So there we have the hole. You can see how we've been cutting halfway into the other hole. The boring bar isn't affected quite so much with that. So now I'm going to put the boring bar in. But first I'm going to measure between here and here on each side to make sure that this is exactly central, because now is the time to shift it one way or the other. I don't care this way, but this way is important because there's very little left. For the first cut, I have to make sure this doesn't grab onto the hole. You can hear how far out that hole was pushed when I drilled it. This is the fitted wrist pin brass, one of 4. They've been heated up and split so that there's the bearings are individual now. The wedge fits through underneath. It actually has a hole in the bottom that bolt goes up into, and we'll tighten it up for you. And the brasses are just as you saw them being made. So we'll do 3 more of these and I'll have it done. So this is it for the conrod series. We've made 2 more new conrods. They're identical to the one original that we started to. This connecting rod at the back here is the original rod that came with number 1 engine. It had no brasses, but it has the original strap, new bolts, new brasses, new pins, and it's fairly straight, so it's good enough to use. This rod is a replacement. These other 3 are basically copies of this one rod. This one's the mate. This is the mate for the original rod. It's the other side. And then there's the 2 that you've watched us making.
for the complete rods on the other engine. All complete with their brasses. Everything's ready to go. Everything's fitted. So I hope you enjoyed it.
Thanks for watching right to the end of the video. If you enjoyed yourself, leave me a comment and hit that like button. And if you're new, here are a couple other episodes from the series that you might enjoy.